Hello everyone, today we are going to learn proton NMR spectroscopy. Nuclear magnetic resonance spectroscopy is a technique used to determine the structure of compounds. In this video, we are going to focus on the proton NMR spectroscopy. Even though there are many other spectrometers including carbon NMR, nitrogen NMR, proton NMR was the first and most common atom used in nuclear magnetic resonance spectroscopy. So NMR, how does it work? We have already discussed the principle in the previous video, so we will just recollect it. The atomic nucleus is a spinning charged particle and it generates a magnetic field. In the absence of an external applied magnetic field, the nucleus spins in random direction. But when an external magnetic field is present, the nuclei align themselves either with or against the magnetic field. So, depending upon that, it leads to the formation of splitting of energy level. The energy difference is delta E. Delta E is the difference in energy between alpha and beta spin states. This depends upon the applied magnetic field as shown in the graph. The greater the strength of applied magnetic field, the larger will be the splitting. So the larger will be the delta E value. So when radiation, the applied radiation, that is RF frequency applied, when it matches with the delta E value, the spin flipping occurs. That means the change of spin of nucleus from alpha state to beta state. So the transition occurs. Then it goes to the higher energy, beta spin state. So then relaxation occurs. So relaxation is when the nuclei return to their original state. So in this process they emit electromagnetic signal whose frequency depend upon the delta E value as well. The proton NMR spectrometer reads these signals and plots them in the graph and gives us the NMR spectrum. So the relaxation process that is monitored here. So that is, in other words, that is called as free induction decay. So that is monitored and recorded. That gives us the NMR spectrum. So what are the information that we get from the NMR spectrum? So first we get the information about the number of signal, position of signal, integration, that is intensity of NMR signals. Then we are also getting the information from splitting of signal. So let us see them in detail one by one. Number of signals. So there are different protons present in a given molecule, so that each and every proton resonate with different frequency. Hence we get various number of signals. So how do we first determine how many equivalent protons are there in a given molecule? So there are many ways to determine how many sets of equivalent protons there are in a molecule. For example, determining how many equivalent protons there are is to look at the atom attached to the proton, usually carbon, and observe what that atom is bonded to, and then the atom bonded to that. So like that we have to find out the equivalent protons. So if they are attached to similar atoms, that means they are all equivalent. If there is no difference, then we are assuming it as equivalent protons. If there is a difference, then we say that it is non-equivalent protons. The other way is to find out replacing the proton with deuterium to form two different molecules. If the two different molecules are same, then we can say that these two protons are equivalent. If not, then they are non-equivalent. So are protons on the same carbon atoms always equivalent? The answer is no. So if you consider this compound, so if you consider these two hydrogens, they are equivalent or not. That's what we are going to check now. So you first replace the first hydrogen by deuterium and the second hydrogen by another deuterium molecule and get two different molecules. If these two different molecules are same, then we can say that these two compounds are these two protons are equivalent. So here if you see the first compound, deuterium is now trans to cis, trans to bromine and cis to chlorine. So if you see the second compound where the deuterium is cis to bromine but trans to chlorine. So these two molecules are different. That indicates that these two protons are non-equivalent. So this is how you have to first determine the protons, whether they are equivalent or not. So this is the best way to find out whether the proton is equivalent or not. So then we have to determine how many signals are possible for a particular molecule. So consider this chlorocyclobutane molecule. So now you have to first check how many protons are possible for this compound. So here one kind. So you have these two hydrogens are of one kind and these two hydrogens are of one kind. So totally we can expect if you consider the stereochemistry and everything, then we can expect 5 signals for this compound. So after checking the equivalent carbons, the number of carbon, then we have to check for its position. So the position of signal is also very important. So the position of the signal in an NMR spectrum are based on how far they are from the signals of the reference compound. So this information tells us that what kind of a proton or protons that are responsible for the particular signal. So TMS is normally used as reference. So it can be easily removed from the sample by evaporation due to its volatile properties. So TMS is resonates as at lower frequency than most other signals. So there are plenty of reasons for choosing TMS as the solvent. So tetramethylsilane is usually used as a reference compound because it can easily be removed from the sample by evaporation due to its volatile properties. TMS is absorbed at upfield region than the most other signals of any other molecule because its methyl protons are in a more electron dense environment than most protons of any other organic molecules. And also it has 12 protons in it, 4 methyl groups, so 4 3s are 12 protons. So it is giving highly intense peak So that can be a good reference for NMR, proton NMR spectral analysis. So chemical shift. So it's a measure of how far the signal produced from the proton is from the reference compound signal, and is usually measured with in terms of delta scale. The TMS or the reference compound is observed at 0 delta on the very left of the spectrum, and it moves towards a left. The ppm values become larger. ppm stands for parts per million, and it is the unit used to measure the chemical shift. The proton chemical shifts range from 0 to 15 ppm. The chemical shift is identical for a specific proton regardless of the spectrometer used. The formula for calculating the chemical shift is distance download from TMS. So chemical shift can be given by frequency of signal minus frequency of reference divided by spectrometer operating frequency. The whole thing we have to multiply it by 10 to the power 6. So here you have to know the concept of shielding. Actually, whatever the magnetic field we apply, that cannot be recognized by the proton because of the electron that revolves in the nucleus. So shielding affects the chemical shift. The shielding is different for different protons in a molecule, and that is why there are many signals in the proton's NMR signal instead of just one. In a magnetic field, electrons go around the nuclei and induce a local magnetic field that opposes the applied magnetic field. So the effective magnetic field, this is what the nuclei sense through its electron filled environment. So B effective is equal to B applied minus B local, where B applied is the magnetic field that we apply. So B local is the magnetic field supplied by the surrounding electrons around the nuclei. This number varies between nuclei in the molecule. According to this formula, the greater the electron density is around the nuclei, the larger the B local will be, and the more the proton is shielded from the applied magnetic field. This is called as diamagnetic shielding. Protons in electron dense environment sense a smaller effective magnetic field because they are more shielded by the large amount of electrons, and therefore will require a lower frequency to come into resonance because the delta E is smaller. The delta, obviously the delta value will also be smaller, and lower frequencies are located on the right side of the spectrum, that is upfield region, farther to the right hand side of the spectrum. Protons in electron poor environment sense a larger effective magnetic field because they are less shielded due to fewer electrons, and therefore they require a higher frequency to come into the resonance because delta E is larger. Now delta value will also be larger, and higher frequencies are located on the left side of the spectrum. So this is called as downfield, that is observed farther to the left side of the spectrum. So the electronegativity of an atom that will affect its chemical shift value. So the electron cloud shields the nucleus from applied magnetic field. That's what we discussed so far. So electron negativity that will affect the chemical shift. So how does electronegativity affect chemical shift? So how do you define electronegativity? So electronegativity is defined as the tendency of an atom to pull electron towards itself. Therefore, electronegative atoms remove electron density from the proton. This causes proton to have less electron density, and this leads to less shielding. If the proton has less shielding, it will feel the applied magnetic field more, and this leads to higher delta E value and higher delta value, that is higher chemical shift. So protons that are closer to the electronegative atom are in less electron dense environment, which means that they are their chemical shift values will be larger. So that is why normally CH2, that is methylene group, that will be observed around 1.1 if it is purely attached to carbon environment. So if it is attached to oxygen, that is CH2O, that is the methylene proton will be observed at around 4 delta. So protons that are closer to the electronegative atom, maybe oxygen atom or nitrogen atom, then the electron density around that proton will be less. That leads to larger chemical shift value. So methyl proton is expected to be observed at 0.9 to 1.2 delta. It's a sp3 hybridized proton. If you compare this with sp2 hybridized alkene and sp hybridized alkynes, here we have 25% of S character in the case of sp3 hybridized carbon. So if more the S character, we all know that more the S character, the more will be the electronegativity. Hence we expect sp hybridized carbon, that is alkyne, acetylene for example, that will be having free hydrogen atom. Hence it will be observed in upfield region. However, if you compare the chemical shift value of alkane, alkene and alkyne, the order is different. So sp3 hybridized proton, it is observed at 0.9 to 1.2 delta. sp hybridized alkyne is observed at 2 to 3.5 delta. So here it looks like it deviates from our point what we discussed so far. But these values can be justified by looking at the orientation of pi electrons, that is how the pi electron circulates under the influence of applied magnetic field. Here comes the concept of magnetic anisotropy. That is, if you measure the magnetic properties in different directions, you will experience different magnetic field. That is, magnetic field changes with respect to the direction. This is called as magnetic anisotropy. So this helps us to compare the values of chemical shift. Consider the alkene. Here pi electron develops an induced magnetic field in the presence of applied magnetic field. This induced magnetic field is right angles to the applied magnetic field. This induced field opposes the magnetic field near carbon, whereas it aligns near hydrogen. Hence, the protons will feel greater field strength and hence resonates at a lower applied magnetic field, that is downfield. It's observed at 4.6 to 5.8 delta. However, the circulation of the induced magnetic field in the case of alkyne is of a different direction. It opposes near proton. When the axis of alkyne group lies parallel to the direction of applied field, the pi electrons are induced to circulate around the axis in such a way that the induced field opposes the applied field. Thus, protons feel smaller field effect and resonates at higher applied field, that is upfield. So, in the range of 2 to 3.5 delta. Similarly, in the case of benzene, the pi electrons are delocalized cylindrically over the aromatic ring. This produces a ring current. The induced current is opposing the magnetic field in the center of the ring and it is aligned outside the ring. Thus, aromatic protons experience a magnetic field greater in magnitude than the applied field. Such protons are said to be de-shielded and hence smaller applied field will be required to bring them to resonance. Hence, it is observed at downfield region. So, that is in the range of 6.5 to 8.5 delta. Hence, from the NMR spectrum, from the position of signal, we can come to the conclusion about the nature of proton that is present in that particular organic compound or any compound. So, next one is integration or intensity of NMR signals. So, integration is the area measurement that tells us the relative number of protons that give rise to each signal. The area under each signal is proportional to the amount of radio energy and number of equivalent protons that give rise to that particular signal. The numbers do not always correspond to the exact or absolute number of protons. Instead, it tells us the relative number of the amount of equivalent protons. So, next one is splitting of signal. This is very important feature that will help us to find out the nature of protons and the neighboring protons. Because splitting of signal is caused by protons bonded to adjacent carbons. Proton NMR always follow n+1 rule. N is the number of equivalent protons that are bonded to the adjacent carbon. So, the number of splitting that occurs is 1 more than the number of equivalent protons bonded to the adjacent carbon. If the adjacent carbon has 3 protons, then it will be split into 4 peaks. So, that is observed as quartet. Similarly, if it is attached to 2 protons, then we will be getting 3 signals. The peak will be split into 3. That means triplet. So, here we should know about the multiplicity, the term called multiplicity. So, that is the number of peaks in a signal. The number of protons bonded to the immediate carbon, that is the adjacent carbon, determines the multiplicity. That is whether it is a singlet, that means a single proton. If there is two signal, then it is called as doublet. If three, then it is called as triplet. If it is split into four, then it is quartet. If it is more than that, then it is called as multiplet. That is called as spin multiplicity. So coupled proton. What do you mean by coupled proton? The splitting is always mutual. That is, they are the protons that split each other's signal. That is called as coupled proton. Spin-spin coupling. Different kinds of protons are close enough for their magnetic fields to influence on each other. The spin of one nucleus influences the spin of another nucleus. That is called as spin-spin coupling. This is possible when both are close enough. Even sometimes it happens when they are separated by more than 3 bonds. That is called as long range coupling. Due to this, sometimes a small splitting will be observed. Coupling constant. This is the distance between two adjacent peaks of a split signal. A signal is split into two peaks. That means the distance between these two peaks, these adjacent peaks, are denoted by the letter J. That is called as coupling constant. The magnitude of J is a measure of how strongly the nucleus spin of the coupled proton influence each other. Therefore, it is dependent upon the number and type of bonds that connect the coupled protons and their geometric relationship. Therefore, for some molecules, the trans form could be creating a smaller coupling constant than the cis form. So, what are the rules for proton-proton spin-spin coupling? So, only non-equivalent protons couple. Equivalent protons are in the same environment and their signal overlap. So, only non-equivalent protons can split signals. So, protons that are separated by more than 3 single bonds do not couple because they are not close enough to each other. Hence, because there is no influence by each other's magnetic field, and signals for OH and NH are usually observed as singlets. Keeping all these points in mind, we can easily derive the structure of unknown compound provided if we have the proton NMR spectrum of that particular compound. Earlier I have also given one more video on how to solve the structure of unknown molecule by using the spectral data. Kindly refer that as well. Okay. With this message, I am leaving from this video lecture. So we will meet again.